Computer data storage, often called storage or memory, is a technology consisting of computer components and recording media used to retain digital data. It is a core function and fundamental component of computers. The central processing unit of a computer is what manipulates data by performing computations. In practice, almost all computers use a storage hierarchy, which puts fast but expensive and small storage options close to the CPU and slower but larger and cheaper options farther away. Often the fast volatile technologies are referred to as memory, while slower persistent technologies are referred to as storage. However, memory is sometimes also used when referring to persistent storage. In the von Neumann architecture, the CPU consists of two main parts: control unit and arithmetic logic unit. The former controls the flow of data between the CPU and memory, while the latter performs arithmetic and logical operations on data. Functionality. Without a significant amount of memory, a computer would merely be able to perform fixed operations and immediately output the result. It would have to be reconfigured to change its behavior. This is acceptable for devices such as desk calculators, digital signal processors, and other specialized devices. Von Neumann machines differ in having a memory in which they store their operating instructions and data. Such computers are more versatile in that they do not need to have their hardware reconfigured for each new program, but can simply be reprogrammed with new in-memory instructions. They also tend to be simpler to design, in that a relatively simple processor may keep state between successive computations to build up complex procedural results. Most modern computers are von Neumann machines. Data organization and representation. A modern digital computer represents data using the binary numeral system. Text, numbers, pictures, audio, and nearly any other form of information can be converted into a string of bits, or binary digits, each of which has a value of 1 or 0. The most common unit of storage is the byte, equal to 8 bits. A piece of information can be handled by any computer or device whose storage space is large enough to accommodate the binary representation of the piece of information, or simply data. For example, the complete works of Shakespeare, about 1250 pages in print, can be stored in about 5 megabytes with 1 byte per character. Data is encoded by assigning a bit pattern to each character, digit, or multimedia object. Many standards exist for encoding. By adding bits to each encoded unit, redundancy allows the computer to both detect errors in coded data and correct them based on mathematical algorithms. Errors generally occur in low probabilities due to random bit value flipping, or physical bit fatigue. Loss of the physical bit in storage, its ability to maintain distinguishable value, or due to errors in inter- or intra-computer communication. A random bit flip is typically corrected upon detection. A bit, or a group of malfunctioning physical bits, is typically automatically fenced out, taken out of use by the device, and replaced with another functioning equivalent group in the device, where the corrected bit values are restored. The cyclic redundancy check method is typically used in communications and storage for error detection. A detected error is then retried. Data compression methods allow in many cases to represent a string of bits by a shorter bit string and reconstruct the original string when needed. This utilizes substantially less storage for many types of data at the cost of more computation. Analysis of trade-off between storage cost-saving and costs of related computations and possible delays in data availability is done before deciding whether to keep certain data compressed or not. For security reasons, certain types of data may be kept encrypted in storage to prevent the possibility of unauthorized information reconstruction from chunks of storage. Snapshots. Hierarchy of storage. Generally, the lower a storage is in the hierarchy, the lesser its bandwidth and the greater its access latency is from the CPU. This traditional division of storage to primary, secondary, tertiary, and offline storage is also guided by cost per bit. In contemporary usage, memory is usually semiconductor storage, read-write random access memory, typically DRAM or other forms of fast-bit temporary storage. Storage consists of storage devices and the media not directly accessible by the CPU, typically hard disk drives, optical disk drives, and other devices slower than RAM but non-volatile. Historically, memory has been called core, main memory, real storage, or internal memory. Meanwhile, non-volatile storage devices have been referred to as secondary storage, external memory, or auxiliary, peripheral storage. Primary storage, often referred to simply as memory, is the only one directly accessible to the CPU. The CPU continuously reads instructions stored there and executes them as required. Any data actively operated on is also stored there in uniform manner. Historically, early computers used delay lines, Williams tubes, or rotating magnetic drums as primary storage. By 1954, those unreliable methods were mostly replaced by magnetic core memory. Core memory remained dominant until the 1970s, when advances in integrated circuit technology allowed semiconductor memory to become economically competitive. This led to modern random access memory. It is small-sized, light, but quite expensive at the same time. As shown in the diagram, traditionally there are two more sublayers of the primary storage besides main large-capacity RAM. Processor registers are located inside the processor. Each register typically holds a word of data. CPU instructions instruct the arithmetic and logic unit to perform various calculations or other operations on this data. Registers are the fastest of all forms of computer data storage. Processor cache is an intermediate stage between ultra-fast registers and much slower main memory. It was introduced solely to improve the performance of computers. Most actively used information in the main memory is just duplicated in the cache memory, which is faster, but of much lesser capacity. On the other hand, main memory is much slower, but has a much greater storage capacity than processor registers. Multi-level hierarchical cache setup is also commonly used, primary cache being smallest, fastest and located inside the processor, secondary cache being somewhat larger and slower. Main memory is directly or indirectly connected to the central processing unit via a memory bus. It is actually two buses, an address bus and a data bus. The CPU firstly sends a number through an address bus, a number called memory address, that indicates the desired location of data. Then it reads or writes the data in the memory cells using the data bus. Additionally, a memory management unit is a small device between CPU and RAM recalculating the actual memory address. For example, to provide an abstraction of virtual memory or other tasks. As the RAM types used for primary storage are volatile, a computer containing only such storage would not have a source to read instructions from, in order to start the computer. Hence, non-volatile primary storage containing a small startup program is used to bootstrap the computer, that is, to read a larger program from non-volatile secondary storage to RAM and start to execute it. A non-volatile technology used for this purpose is called ROM, for read-only memory. Many types of ROM are not literally read-only, as updates are possible, however it is slow and memory must be erased in large portions before it can be rewritten. Some embedded systems run programs directly from ROM, because such programs are rarely changed. Standard computers do not store non-rudimentary programs in ROM, and rather use large capacities of secondary storage, which is non-volatile as well, and not as costly. Recently, primary storage and secondary storage in some uses referred to what was historically called, respectively, secondary storage and tertiary storage. Secondary storage. Secondary storage differs from primary storage in that it is not directly accessible by the CPU. The computer usually uses its input-output channels to access secondary storage and transfers the desired data using intermediate area in primary storage. Secondary storage does not lose the data when the device is powered down. It is non-volatile. Per unit, it is typically also 2 orders of magnitude less expensive than primary storage. In modern computers, hard disk drives are usually used as secondary storage. The time taken to access a given byte of information stored on a hard disk is typically a few thousandths of a second, or milliseconds. By contrast, the time taken to access a given byte of information stored in random access memory is measured in billionths of a second, or nanoseconds. This illustrates the significant access time difference which distinguishes solid-state memory from rotating magnetic storage devices. Hard disks are typically about 1 million times slower than memory. Rotating optical storage devices, such as CD and DVD drives, have even longer access times. With disk drives, once the disk read-write head reaches the proper placement and the data of interest rotates under it, subsequent data on the track are very fast to access. To reduce the seek time and rotational latency, data are transferred to and from disks in large contiguous blocks. When data reside on disk block, access to high latency offers a ray of hope in designing efficient external memory algorithms. Sequential or block access on disks is orders of magnitude faster than random access, and many sophisticated paradigms have been developed to design efficient algorithms based upon sequential and block access. Another way to reduce the I/O bottleneck is to use multiple disks in parallel in order to increase the bandwidth between primary and secondary memory. Some other examples of secondary storage technologies are flash memory, floppy disks, magnetic tape, paper tape, punched cards, standalone RAM disks, and I/O megazip drives. The secondary storage is often formatted according to a file system format, which provides the abstraction necessary to organize data into files and directories, providing also additional information describing the owner of a certain file, the access time, the access permissions, and other information. Most computer operating systems use the concept of virtual memory, allowing utilization of more primary storage capacity than is physically available in the system. As the primary memory fills up, the system moves the least used chunks to secondary storage devices, retrieving them later when they are needed. As more of these retrievals from slower secondary storage are necessary, the more the overall system performance is degraded. Tertiary storage or tertiary memory provides a third level of storage. Typically, it involves a robotic mechanism which will mount and dismount removable mass storage media into a storage device according to the system's demands. This data is often copied to secondary storage before use. It is primarily used for archiving rarely accessed information since it is much slower than secondary storage. This is primarily useful for extraordinarily large data stores, accessed without human operators. Typical examples include tape libraries and optical jukeboxes. When a computer needs to read information from the tertiary storage, it will first consult a catalog database to determine which tape or disk contains the information. Next, the computer will instruct a robotic arm to fetch the medium and place it in a drive. When the computer has finished reading the information, the robotic arm will return the medium to its place in the library. Tertiary storage is also known as nearline storage because it is near to online. The formal distinction between online, nearline, and offline storage is: online storage is immediately available for I/O. Nearline storage is not immediately available, but can be made online quickly without human intervention. Offline storage is not immediately available, and requires some human intervention to become online. For example, always-on spinning hard disk drives are online storage, while spinning drives that spin down automatically, such as in massive arrays of idle disks, are nearline storage. Removable media such as tape cartridges that can be automatically loaded, as in tape libraries, are nearline storage, while tape cartridges that must be manually loaded are offline storage. Offline storage is a computer data storage on a medium or a device that is not under the control of a processing unit. The medium is recorded, usually in a secondary or tertiary storage device, and then physically removed or disconnected. It must be inserted or connected by a human operator before a computer can access it again. Unlike tertiary storage, it cannot be accessed without human interaction. Offline storage is used to transfer information, since the detached medium can be easily physically transported. Additionally, in case a disaster, for example a fire, destroys the original data, a medium in a remote location will probably be unaffected, enabling disaster recovery. Offline storage increases general information security, since it is physically inaccessible from a computer. Data confidentiality or integrity cannot be affected by computer-based attack techniques. Also, if the information stored for archival purposes is rarely accessed, offline storage is less expensive than tertiary storage. In modern personal computers, most secondary and tertiary storage media are also used for offline storage. Optical disks and flash memory devices are most popular, and to much lesser extent removable hard disk drives. In enterprise uses, magnetic tape is predominant. Older examples are floppy disks, zip disks, or punched cards.